Hi everyone. In our last video, we solved a distance minimization problem, and this time we'd like to solve an area maximization problem. So the statement of our problem is this. We wish to find the dimensions of the rectangle of greatest area that could be inscribed within the ellipse x squared plus y squared over 9 equals to 1. So in all of these applied optimization problems, the first step is generally to draw a picture to help us set up the relevant equations to help solve the problem. And in this case, of course, we have an ellipse that's in standard form with center at the origin. And so this ellipse is going to be symmetric about both the x and y axes. So here's our xy plane, and we know that the x-intercepts will be at plus or minus 1. And so here we indicate those values on the x-axis, right? If y is either plus or minus 3, then x is 0. Therefore, we have those two y-intercepts, plus 3 and minus 3. Okay, and so with those 4 points, gives us enough information to just kind of draw a rough sketch of the ellipse relevant to this problem. Okay, so there's our ellipse. So now if we think of again inscribing a rectangle within this ellipse, again because the ellipse is symmetric about both axes, we know that if say this point P happens to be the vertex in the first quadrant, then reflecting about the x-axis, we'll get this point, which will also be a vertex point, and then reflecting either of these points about the y-axis, we should end up with the remaining two vertices of the inscribed rectangle. And so let's use another color to sketch in this inscribed rectangle in the picture. Okay, very good. So here's our rectangle. The problem is to maximize its area. So if we suppose that, again, as we drew in our picture, we have this point P equaling xy is in fact the vertex of the rectangle. It's also in the first quadrant. Okay, then we know, of course, for any rectangle, the area will be the product of its length times its width. Okay, and therefore, in terms of these coordinates, we see that, of course, y represents the height of the point P above the x-axis. So y is essentially this measurement here, right? But of course, this distance, the symmetrical distance, is also y. And therefore, we see the total length of the inscribed rectangle is going to be 2y. And similarly, this horizontal displacement of the point P from the origin represents the x-coordinate of P. So this symmetrical distance, also being x, makes the total width of the rectangle, width is 2x. And so therefore, we could write our area formula now as simply the product 2y times 2x. Or in other words, the area is 4xy. Okay, so there's one equation for the area of the rectangle. Now, the only issue we have here with this formula is that it's a function of two variables, x and y. And so to use our derivative theorems to maximize the area, right, we need to go one step further and write the area as a function of only one variable, right? So how do we do that? Well, we come back to the original equation of the ellipse, which tells us the relationship between x and y for any point on the ellipse. And so therefore, if we solve the equation star for y to get, okay, y squared divided by 9 would be equal to 1 minus x squared, okay, and so therefore multiply both sides by 9. Y squared is equal to 9 times 1 minus x squared, and we could go further by taking square roots. But remember that y must be positive because y is on the ellipse and it's in the first quadrant. So y is the positive square root of 9 times 1 minus x squared, okay, which means that the square root of 9 is 3. So we could further simplify this formula as 3 times the square root of 1 minus x squared. Okay, or if we'd like, right, we could replace the radical by the 1/2 power. So y must be 3 times 1 minus x squared to the power of 1/2. Okay, and so what's left? Well, now, right, we're substituting for y back into the area formula for the inscribed rectangle. So if we call these equations, let's say 1 and 2, then we can immediately write the area now by substituting for y from equation 2 into 1 to get ultimately that the area is going to be 4x times y, right? Well, 4 times 3 is going to be 12x times the y, well, what's it, 3 times the 1 minus x squared to the 1/2 power. Okay, so this would be an expression for the area, therefore, of the inscribed rectangle only dependent on the variable x. And what is the range of x? Right, again, because x is on this, is the x coordinate of this point on the ellipse in the first quadrant, x must be positive, and x could not exceed 1, right? For 0 less than x less than 1. So these would therefore be the constraints on x. And so now it's just a matter of using calculus, right, to find the critical value of x, which will in fact maximize the area of our rectangle. And so our next step is to differentiate. So now we find that a prime of x, well, to find that, we need to use the product rule for differentiating. So well, let's just write that down because it's hard to see the formula from the other side of the page. So a prime of x would be the derivative of, say, 12x times 1 minus x squared to the power 1/2. It's the derivative of that product. And so that would give us, say, by the product rule, the first factor, 12x, times the derivative of the second factor. But this second factor involves the chain rule to differentiate, right? Because it's a function raised to a power. So we take our power, 1/2, times the base function to the power minus 1. So 1/2 minus 1 would be a negative 1/2. But then by the chain rule, right, we still have to differentiate this base function, and the derivative of 1 minus x squared would be negative 2x. Okay, so that's the first times the derivative of the second, and then of course plus our second function, 1 minus x squared to the 1/2 times the derivative of 12x, which will be 12. Okay, so now let's see, can we simplify this formula? And of course we can. Well, we see, okay, in the first term in the sum involves a factor of 1/2 and a 2, right? So those would kind of cancel each other out, and then we'd have a negative 12 x times x squared, right? And now instead of writing the 1/2 power, we could go back to radical notation. And because of the negative exponent, right, that's going to place 1 minus x squared in the denominator to the 1/2 power, or in other words, 1 over the square root of 1 minus x squared. Okay, and then the rest, right, the second term in the sum, 12 times the square root of 1 minus x squared to the 1/2, square root of 1 minus x squared, or 1 minus x squared to the 1/2 power. So that would just be right, rewriting, right, the derivative in somewhat simpler form and going back to the radical notation. Now, of course, we'd like to simplify a little further, and that would involve writing this expression for the derivative of area as a single fractional expression. So to do that, we need the common denominator, which in this case will be root 1 minus x squared. So multiplying by root 1 minus x squared over itself by the second term in the sum, we now have the simplified formula minus 12x squared plus 12 times 1 minus x squared all over the common denominator of square root 1 minus x squared. So let's now combine, when we distribute this 12 in the numerator, right, across that second factor in the product, and then combine like terms. So we'll have, a constant 12. We have this minus 12x squared, another minus 12x squared. So in fact, a negative 24x squared, all divided by root 1 minus x squared. Okay, and so let's factor out the 12 in the numerator to write 12 times 1 minus 2x squared all over the square root of 1 minus x squared. Okay, so that would be our simplified formula here for the derivative of area. So it was a little bit of work because, we had to use the product rule and then also the chain rule and the derivative, and then there was a little bit of algebra to simplify the formula as much as possible. Now we know that, remember, the denominator, root 1 minus x squared, that will always be positive in our problem because, remember, the x value is a number that lies between 0 and 1 as it's the x coordinate of that point P. Okay, so the denominator is always positive. So therefore, the only way we could get a critical number is if the numerator is 0. So we see that a prime of x will equal to 0. Therefore, if and only if 1 minus 2x squared, right, if that factor was going to equal to 0, so that would require that 2x squared equals to 1, right? 1 equals 2x squared. 2x squared equals 1. Solving for x, first of all, x squared is 1/2. And again, because x is positive, means that x must be in our problem the positive square root of 1 over radical 2, right? So this would be the only critical number for the function, the area function. We use the critical number, right, to split up the domain of area, which was just, along the x-axis, right? The domain was for x was only between 0 and 1. So here we have the number 1 over radical 2. Remember, radical 2 is about 1.41. So this would be equivalent to radical 2 over 2, right? Or about half of that. In other words, about 0.7. And so now let's just think about, again, the derivative of area, a prime of x, right, which is given by this formula. We see for any value of x smaller than 1 over radical 2. So like, for instance, if you put in 1/2, let's say, for x, right, then the numerator becomes 12 times 1 minus 2 times a fourth, right, 12 times 1 minus a half, right, positive value, obviously. The denominator is always positive, so the ratio of two positives is positive, right? So a prime is always positive here, and so that implies that a prime is always positive, which implies that the area function is increasing, right? Because again, it always has positive slope on that interval, right? And so its graph is always rising. So the area is increasing on this interval from 0 to 1 over root 2. On the other hand, if you plug in any value for x between 1 over radical 2 and 1, okay, of course, when you square that x, it will be greater than 1/2, which is the square of 1 over radical 2. And so now if you multiply 2 by a number greater than 1/2, that product is going to exceed 1, which is going to make this derivative of area negative valued. Okay, so the area has the negative derivative on the interval from 1 over radical 2 to 1, which will imply that the area function is decreasing since the area has the negative slope on the interval from 1 over radical 2 up to 1. And so we see that our area function is increasing as the x-coordinate of this point P increases from 0 to 1 over radical 2, and then decreases as x continues to increase from 1 over radical 2 to 1. So therefore, the area is maximized. A is maximized when x is exactly 1 over radical 2. And so what does that tell us then about the y-coordinate of our point P? Well, if you remember here, right, from formula 2, y was 3 times the square root of 1 minus x squared. So we could say then from equation 2, y must be 3 times the square root of 1 minus, and of course the square of 1 over radical 2 is 1/2. So that's 3 times the square root of 1/2, or in other words, 3 times 1 over radical 2. In other words, 3 divided by the square root of 2. And therefore, the dimensions of the optimal inscribed rectangle are going to be given as, okay, the length, remember, is going to be 2 times y, right, which is 2 times 3 over radical 2. Now, you could think of 2 as the square root of 2 times itself. Okay, so then when you simplify this product, right, you could cancel one of these radical 2's. So the length will be 3 root 2 units long. And as far as the width, the overall width of this inscribed rectangle is 2x. right? So it's 2 times 1 over radical 2. Or again, root 2 times root 2 times 1 over radical 2. Again, cancel 1 over radical 2. So the overall width is simply radical 2 units. Okay, and so this is the solution method for this uh, this maximization problem. The first thing, again, we drew a diagram of the ellipse with an inscribed rectangle. We wrote down the formula for the area of the inscribed rectangle based on the xy coordinates of the vertex point P in the first quadrant. We found how we could replace y in terms of x, and then obtain just a function of only x to be optimized. And we used our first derivative test to conclude that when x is 1 over radical 2, the area would be a maximum. And then just computing the overall length and width of that optimal rectangle. So this is my second optimization problem. We'll have one more to look at, which would involve maximizing the volume of a solid. So we'll see you next time. Goodbye.